Good afternoon, everyone. I hope you're enjoying the conference. I'm Fsihi, and here's the plan of my presentation. It is divided to 3 parts. First, introduction, which itself consists of 2 parts, history of the problem and research innovativeness. Second, material and methods in which math model and solution method is discussed. And the third one is results. The study of the dynamics of fluid conveying pipes started in 1960s. However, 2 basic aspects of the problem have been known for a long time, and almost everyone has an experience of them. One of that basic aspect is buckling of the pipe. It is the reason why the significant force is needed to control the middle of the fire hose. And the other one is the flutter of a cantilever pipe, as observed in the snaking motion of the garden hose when it's dropped on the ground. In fact, these 2 phenomena are sometimes referred to fire hose instability and garden hose instability, respectively. Research in rotor dynamics also has a long story, starting Rankin's paper on the whirling motion of a rotor in 1869. Lateral motion of rotors are in the form of whirling motion, which is a planar motion. These 2 videos show the different whirling motion of the rotor. In rotor dynamics, the rotating speed that produce resonance responses are called critical speeds. At these speeds, the rotor has high amplitude motion in transverse directions. The major concern of research is to predict critical speed and prevent their associated high amplitude motions. There are great many engineering applications of fluid conveying pipes, and therefore, fluid-induced vibration of these pipes has been extensively studied in the past decades using fluid structure interaction method. By fluid structure interaction, we mean that the method that focuses on the buckling and flutter of pipes, which only depends on the fluid excitation. However, for some pipes accompanied by spinning motion, additional forces are added to the systems in addition to the fluid-induced forces. So the goal here is to develop mathematical model for these systems and to investigate their dynamics. And to do so, we need to use combination of FSI theories and also theories of rotor dynamics. The model introduced in this study is a horizontal pipe that's simply supported. The system is considered a tubular beam rotating about its longitudinal axis with a rotational velocity of omega, as well as carrying a fluid which has a velocity of u. To derive equation of motion, 2 coordinate system is set, as shown in the figure, an inertial and a rotating frame. First, displacement as well as velocities were calculated with respect to the rotating frame, and then kinetic energy and potential energy of the system were calculated, and finally, mathematical model of the system is obtained using Hamilton method. And the partial differential equations governing motions in 2 lateral directions are derived by employing Euler-Bernoulli beam theory. These 2 equations governing displacement of the 2 lateral directions, namely V and W, are these equations. Galerking method is a conventional tool for transferring PDs to a set of ODEs. For this system, equation of 2 transverse motions is like these functions, where phi are appropriate comparison functions satisfying the boundary condition of the problem, and q's are generalized coordinate of the discretized system. By using this method, the equation of motion would be like this, where M, G, C, K are mass, gyroscopic, damping, and stiffness matrices. And N is nonlinear vector. If we assume there is no flow velocity in the system, it is degraded to a rotor. However, this rotor is described in the rotating frame and not in the inertial frame. To see the rotational speed affect, how rotational speed affect the motion in the rotating frame, 2 cases are compared. non-spinning case and a spinning case with a small rotational speed. The motion of these two cases looks like this. These figures show how the evolution of the system's configuration through one period is. Starting from light gray, the color darkens as the time progresses. We call this period fundamental period, and as it has nothing to do with the rotation and depends only on the physical property of the system. For non-spinning case, since there is no rotation, it makes sense that when the system is perturbed in only Z direction, it will vibrate only in that direction. However, for the second case, since there is a small rotation speed, when the system is perturbed in Z direction, the fundamental period ends with the same flexion value, but rotates the clockwise direction relative to the starting point. This is because we are in the rotating frame and the plot is also in the rotating frame, which has rotated a little bit counterclockwise during this period. This is the direction of omega as shown in the schematic of the system. If we continue the time for this configuration, they look like this. The time history of midpoint of the system is shown in these figures. For the first case, it has periodic motion only in Z direction, but for the second case, it has a pulsating motion. Based on these responses, the frequency of these two cases are calculated using FFT. It shows that in non-spinning case, the system has a single frequency of 9.86, colored in purple. It's a counterpart to the fundamental period and has nothing to do with the rotation and depends only on the physical property of the system. It's the natural frequency of the first mode of the simply supported beam, which analytically can be obtained as p to the power of 2. We call it fundamental natural frequency. In the spinning case, however, the pulsating motion necessitates the existence of two periodic motion with closed periods whose superposition produce the pulsating motion. If these two frequencies are calculated for other values of rotational speed, as shown in the figure, it is observed that by increasing the rotational speed, one of them decreases and the other one increases. From these values, it is concluded that they have the general form of this, or more precisely this. The figure also shows that the omega equals to pi to the power of 2. At this speed, one of these frequencies becomes 0 and the other one has 0 amplitude. This means there is no motion in the system. What exactly happens when the system, when the time it takes for the system to make a full turn is exactly the same as the fundamental period. In other words, the rotational speed matches the fundamental natural frequency. This is the critical speed. These two figures show the motion of the system a little bit below and above the critical speed, where the motion is forward and backward respectively. Frequencies obtained above were calculated using FFT tool based on the result of the numerical simulation. However, in the general form, the frequencies of the system can be obtained directly from equation of motion. The variation of natural frequency with respect to rotational speed is plotted here, and it is called frequency analysis, or also known as Campbell diagram in the terminology of rotor dynamics. Frequency analysis shows that due to the presence of the damping, the natural frequencies of the system have complex form. The real part of them denotes the natural frequency itself, and the imaginary part is proportional to the damping. It can be deduced from this equation that imaginary part of the frequency defines if the amplitude is growing or decaying, depending on if it has a positive or negative value respectively. The figure shows that at the critical speed, the imaginary part changes sign and goes from positive to negative. It means that the mode loses its stability. When the critical speed is below the critical speed and the system is disturbed, it's eventually settled back to its original zero equilibrium position because of the damping. On the other hand, when the rotational speed exceeds the critical speed, the system will stabilize at a non-zero position. This section is divided to two parts. First, we'll look at the non-spinning case and then spinning case. If we assume there is no rotational speed in the system, it is degraded to a pipe. The dynamic of this system is well known. Frequency analysis shows that the frequencies decrease with increasing the flow velocity. Numerical simulation also confirms that. The figure of imaginary part shows that for flow velocities higher than the critical speed, zero position is unstable. At these speeds, the system is stabilized at a non-zero position. Frequency analysis for different values of omega shows that increasing rotational speed decreases the critical speed of the system. Numerical simulation also confirms that. This figure shows equilibrium position of the pipe with respect to flow velocity when rotational speed is zero. It shows absolute value of deflection. And this figure shows by increasing the rotational speed, the critical flow velocity decreases. And at omega equals to pi 2, it is zero. Finally, it is important to understand that non-zero equilibrium position are the points that are stationary only in the rotating frame. This means that when the system stops rotating in the rotating frame, it has the rotational speed of omega in the inertial frame. And thank you for your attention.